The next section in chapter 4 is actually going to take a step away from integration for a second. We've spent 2 days doing that. The number one application to integration, which we will eventually learn, is that integration accumulates things. It kind of totals up what's happening. And the number one thing that we accumulate or total is area. So we're going to take a step back from integration and talk about how do we look at area under a curve? What are algebraic ways to establish an estimate for area under a curve, which will eventually lead to what do we do in calculus. So we're going to start with something called a Riemann sum. The word Riemann is name of a mathematician. Years ago, I never mentioned his name. I just talked about how this worked, and then I realized that on the AP test, they always refer to these as Riemann sums. So I want to get in the habit of using that word so you associate it with what I'm going to show you here today. So Riemann did a lot of different things in mathematics, but one of the more basic things he did is he looked at utilizing rectangles to find area under a curve, which hopefully sounds pretty simplistic. So what he realized is if you were drawing rectangles under a curve, you had three different ways that we could draw them. We could do a left end Riemann, or sometimes they're called left hand Riemanns. You could do a right end, or you could do a middle or midpoint Riemann sum. So I want to show you just with kind of a quick example here, and then really I'm going to spend most of my time on Delta Math explaining this because they do a way better job of drawing things than I ever could, of how we actually get this area under the curve. So let's say we are going in with this particular function, we're going from 1 to 4. They have to tell you what part of the curve we're working with. So from 1, which is here, to 4, which is here. So this is the region that I'm trying to find the area of. That's the goal here. And I have to tell you how many rectangles I am partitioning it into. And they will say that. They'll say a number of partitions or a number of intervals. Usually the letter N is involved with a lot of calculus. So let's say we're going to just split it up into 3 rectangles. So you're going to need to know how wide these rectangles should be. Well, if you take your interval, so we'll call this A and B, if we take our interval and subtract it, and then divide by your number of partitions, that's going to tell me how wide each rectangle is. This one I started with a really easy one. We're going 3 units wide. We're splitting into 3 rectangles, so every rectangle is going to be 1 unit wide. And I'll show you on Delta Math how it kind of tweaks it and changes it based on how you want to partition it. So now we got to figure out how high to draw the rectangles to get that height, because if we have width and height, we can multiply them together to get area. And that's where this whole left-right midpoint idea comes in. If you're doing a left Riemann approximation, that means that you're looking at the left side of the interval to draw it. So my first interval goes from 1 to 2. The left side is 1. That's the left side of that first interval. So I want to find where the function is at 1, which in this case it's right on the axis, and I want to draw a rectangle. Well, that's going to seem kind of silly with this first one because there's actually nothing there. But let me show you what happens with the next one. So the next one is the interval from 2 to 3. Let's use the left side to see how tall the rectangle is and then draw it over. So that would be my next rectangle. That one actually does have area. It's this stuff right here. And then my last region, oh, I went too far. Sorry. Got a little excited with my rectangle. Should stop right there. My last rectangle goes from 3 to 4. I want to use the left side, which is the 3 side, to go up to where this function is and level it off, and that gives me this rectangle. That is a left Riemann sum because each interval, so my interval is going from 1 to 2, 2 to 3, 3 to 4, I'm using the left side to determine how high to draw that rectangle. If I did a right Riemann, let me get rid of this. Let me show you how it differs here. So now instead of using the side on the left, so from 1 to 2, instead of using 1, I'm going to go to 2, draw how high it is, and level it off. So that's going to be my first rectangle. From 2 to 3, I'm going to go from 3 all the way to where I hit the function and then level it off. That's going to be my second rectangle. And then from 3 to 4, I'm going to go all the way to the right side, which is 4, level it off, and that gives me my third rectangle. That is a right Riemann sum because I use the right side of the function to determine how high to go. Midpoint's probably what you would expect. Midpoint is not nearly as common, but I will kind of show you just in this picture, and then in delta math make it make a little more sense. Your midpoint is saying instead of using the left side of the interval or the right side of the interval, I want to use the exact middle. So for example, from 1 to 2, the middle of that interval is 1.5. So I'm going to draw in a little altitude here at 1.5, and then I'm going to come across, and that's going to give me my first rectangle. And then I'm going to do the same thing for 2.5, and I'm going to go across, and that's going to give me my second rectangle. It always looks like there's double the rectangles. And then I'm going to go at 3.5 and go across, and that's going to give me my third rectangle. So it takes the middle of each interval all the way up until we hit the function, and that determines the height of each one. So let me show you how we do it on delta math, because their ability to do it and mine is, I think, way, way, way better. So here's one. They have to tell you many things. They have to tell you your interval. So notice that they're writing this as an integral. Your lower number on that integral is your lower part of the interval. So it's starting at 1, and then the upper part is 2.5. I know that notation is not something you're used to, but that's what that is representing. So my lower number on that integral sign is where I'm starting, and my upper is where I'm finishing. It also has to tell you how many partitions I'm doing, and they call them subintervals. So this says we're going to use 3 subintervals to slice it up, and we're going to draw rectangles using a right Riemann approximation. So the first thing you have to do is figure out how wide each interval is going to be. So you're going to take your total distance, so from 1 to 2.5 is 1.5, and you're going to split it into, in this case, 3 rectangles. So 1.5 divided by 3 is 0.5. So I'm going to type in 0.5. And what happens when you do that is that it'll draw these little rectangles, and you can see it starts at 1, it ends at 2.5, these 3 rectangles. Now you have to use your mouse or your touchpad, and you have to drag the right side to get each one to be the correct height. So I want to use, so from 1 to 1.5, I want to use the right side. This always does the opposite that I want. I want to use the right side to get up to that height. And then I have to bring the left side kind of along with it. Then I want the right side. It always does the opposite, always grabs the other one. I want the right side of the second one, and I want to hit the function. And then I want to bring this left side just to meet that same height. And then finally, I want to grab the right side, and then I want the left side to just go to that height. So I am drawing the right side is going to be what determines the height. So let's talk about whether it overestimates or underestimates the area. Now, this one might be pretty obvious to tell that your area under the curve, you actually have a bunch of excess here. You have more than what's actually under this function curve. So we would say that the area is an over approximation or an overestimate. So here's why I know that. Obviously, the picture is big. The key is it increasing or decreasing? If my graph is increasing, then as I go to the right, I'm going to get bigger and bigger values, and it will overestimate it. If it's decreasing, the right side is going to be getting smaller, so the right side will actually underestimate it. So it really depends on 2 things. Is my function increasing or decreasing? And am I looking at the right side or the left side? So we would say that this is an over approximation because the function is increasing. So let me show you a left one. Oh, perfect. So this one is going from 1 to 7. So you can even look on your number line from 1 to 7. We are splitting it up into 4 subintervals. So if I'm splitting from 1 to 7, so 1 to 7 is 6 units wide. And if I'm taking 6 and dividing it by 4, well, 6 divided by 4 is 1.5. And you're welcome to type in a decimal or a fraction. It will put those partitions for you. So if you type something in and the partitions don't go the right way, or they aren't evenly divided, you'll know to fix it. It's not going to let you submit the answer until you do all this. This time I'm using a left Riemann approximation. So that means I'm going to take the left side of each rectangle and go until I hit the function. And then the right side is just going to go to that height. I always have to like grab and drop here. So now my left side of my function, and then the other side is just going to come even. And then the left side, and then this always wants to grab the wrong thing. And then finally the left side, and level this off. So that is a left Riemann approximation because I'm using the left side of the interval going up to the function to determine the height. Now notice this underestimates it because we have all this stuff that we didn't include, all these like white areas. So we would say that it under approximates, and this is because it is still increasing. So if it increasing, the right side is going to be bigger, the left side is going to be smaller, because as it increases, my right side's always going higher than my left. So this is an under approximation because again, it is increasing. If you might want to write down, if it is a right Riemann, you will overestimate it if it's increasing and underestimate it if it's decreasing. If it's a left Riemann, it does the reverse. The left will, if it's decreasing, the left side will overestimate it, and if it's increasing, the left side will underestimate it. See if I can find a midpoint one. Here we go. Midpoint are definitely not as common. They still have to give you a lot of the same information. So this time we're going from 2 to 8, and we're splitting it into 3 partitions, 3 subintervals. So 2 to 8 is 6 units long, split 3 ways. That means each one's going to have a width of 2. So there are my 3 rectangles going from 2 to 8, all split evenly. Midpoint, notice it has this extra dot. That's what's going to, this one's actually easier to draw in Delta Math. That's what's going to go up to my function. So here are my 3. Now, one thing you'll notice with this is you can't really analyze over or under approximations from midpoint, so they will not ask that question. They will only ask that question if you're asked to do a right Riemann or a left Riemann. So then we submit. Let me find one more. Here's a good one. So this is another right one. So this one is going from 0 to that's a midpoint, not a right. I want to do a right or a left. Give me 1 second to find a good one. Now it's going to give me all these midpoint ones. Trap is over and talk about tomorrow. I wanted to see one that was decreasing. I'm getting really picky. Hey, there we go. This is what I want. So this one is a left Riemann. It's going from 1 to 5. It's splitting it into 4 subintervals. So from 1 to 5 is 4 units, split 4 ways. Each one is going to be 1 unit. So nice quick arithmetic there. We are going to do a left Riemann. So we want the left side of each interval. So I'm going to bring this one down. Oh, come down. I'm going to bring this one down till it hits the function. They kind of like lock in place, which is nice. And then I'm going to get the right side to just be the same height. And that also kind of locks in place, and it does a good job of kind of letting it look nice. So my left side was determining the height because it was a left Riemann. And notice that this is over approximating. The reason it's over approximating is my graph is decreasing and I'm using the left side. So the left side's always higher than the right side if I'm decreasing. So we would say this is an over approximation because this left Riemann is working with a decreasing graph. So there you go. I really think Delta Math makes this way easier than I could do by hand, and it really allows you to manipulate a lot without having to draw anything, which I'm incredibly thankful for. We're going to get into more with actual functions, but hopefully this gives you a really nice beginning understanding.